Fantastic, great. Okay, well, so I'm going to talk about, well, the reason Vittorio invited me to this talk was I wrote an article a couple of months ago in the Guardian in their big idea section, and actually, weirdly, for a topic which I thought was kind of an esoteric scientific publication type, inside baseball idea. Actually, one of the most popular articles I've ever written. People still tweet it. Just yesterday, someone was tweeting it, talking about it, and so on. I guess that's in some way the power of the Guardian, but also it's the power of this idea. People are really interested in this idea. A lot of scientists and non-scientists are interested in this particular idea of getting rid of the scientific papers. So what I thought I would do in this talk is give some of the reasons that I talked about in that article, that I think we should do away with scientific papers or make some major changes to the way we do and publish science, and then give some ideas for what we might do afterwards, which is kind of I'll basically give a more in-depth version of this Guardian article that I wrote. So we all know the first scientific journal was this one, the Philosophical Transactions, what's now known as the Philosophical Transactions of the Royal Society, but used to be known as Philosophical Transactions, giving some account of the present undertaking, studies and labours of the ingenious in many considerable parts of the world, which is a less catchy title than the current one, in 1665. As many people have noted, even though we're in 2022 now, we still use many of the features of the paper journal system. We still have volume numbers and page numbers and issues, and we still have objects which are single standalone scientific papers. And I suppose the question is, is there anything advantageous about that we should be keeping when actually we may be able to use our more modern technologies to do something better? And this is one of the examples of one of the very first papers. I don't know, maybe people are familiar with this one, but this is Robert Hooke spotting what people now think, and I believe there's some controversy about exactly what he might have seen, but might think was one of the spots in the belts of Jupiter. This is potentially the first discussion of that through a telescope, through an excellent 12-foot telescope. And that's actually the full scientific paper there. That's all that it was. Just a little, almost, you could almost fit that into a tweet about, I've just seen a spot in one of the belts of Jupiter, which I think is all very well, but we can probably do better than this, and we can evolve somewhat better systems than this. And I started noticing this fairly early in my career, when I tried to correct some scientific papers which had kind of gone slightly wrong. So here's a paper. This is one that was published in the Journal of Nervous and Mental Disease. So I'm a psychologist. I work in a psychiatry center. We do lots of kind of stuff about cognitive behavioral therapy and so on. This is a paper about cognitive behavioral therapy for psychosis. This came out in, a very, it's a very old journal. It's actually a journal not quite as old as the one that we just saw, but a journal that has been around since the 19th century. And it was this exploratory trial that came out. And this paper was, I think it was 2011 or so, 2000, or maybe somewhat after that. This paper was riddled with mistakes. It was riddled with errors, numbers which were impossible, couldn't possibly be real. For example, here's one of the tables. We all know when you're looking at Cohen's d effect size, standard deviation effect size, it would be very weird if the confidence intervals surrounding a Cohen's d effect size were first of all, were this big. I mean, they're dramatically massive confidence intervals, but also, some of them, the confidence interval is the same as the lower part of the confidence interval is the same as the point estimate. These ones are repeated weirdly. These ones, so they're obviously a copy and paste error. At least that's what we thought at the time. And there's various other kind of weird things in this paper, including this graph, which is one of the worst graphs I have ever seen. If you read it there, it's described as histogram with standard error bars showing results on social functioning. Now, you don't have to be an expert statistician to know that that is not a histogram. It also does not have a y-axis. There's nothing on it there, and various other errors in that paper, weird things. So we wrote a letter. Me and some colleagues wrote a letter into that journal to say, perhaps there are some errors in this paper, and perhaps you'd like to correct them. Statistical errors and omissions. So we wrote this letter in. Sorry, it was somewhat later than I said, 2014. And then, instead of correcting those errors, after some time, and this is, after many, many months, they published our letter as a response, and then, so as if we were commenting on the theory or something, we're actually commenting on objective errors and omissions. And then we got a response. They published a second, letter, and that was a response from the original authors, and they said, I can confirm that our findings have been accurately reported. The labeling of the axes on figure 5 is self-evident. Now, just to remind you of what figure 5 looked like, the labeling on that is self-evident, apparently. And that was it. They got one of their statistical editor to look at the paper and so on. And after a long, long time, that paper's still published in that journal. It's still there. No changes made to it. We did our best. And what I'm trying to get across here is that it's incredibly difficult to correct errors, even very obvious objective errors, which everyone in this room, I'm sure, can see that those were objective problems in the paper. It's even hard when the authors don't agree. It's very, very difficult. Now, in those, I think, were just errors of incompetence, whereas there are some errors which are worse than that. So this is Yoshitaka Fuji, who many of you, I'm sure, will know as he's the top of the leaderboard of retracted authors. He's the most retracted scientist of all time. He's had 183 papers retracted from the scientific literature. He was an anesthesiologist who faked trials. As you see, 183 publications out of it. They were all completely fabricated data. And the fascinating thing about this was he did this through the 90s, and a paper came out in 2000, which was titled, it was a letter to the editor, I should say, in the journal Anesthesia and Analgesia. And it was called Reported Data on Granisetron, that's the drug that he was talking about, and Postoperative Nausea and Vomiting by Fuji et al. Are incredibly nice. And they didn't mean incredibly nice as a compliment. What they meant was that the data looked too good to be true. They were too perfect. They were flagging up that these trials, or at least the trial they were talking about, had completely unrealistic data. And you'll notice that the second paper I have referenced there, so this paper came out in 2000. The second paper I've noticed came out in 2000, I've referenced, came out in 2012. And this was an analysis of 168 randomized controlled trials by John Carlisle, who is a kind of a data sleuth, fraud spotting kind of guy in the UK. He's an anesthesiologist himself, I believe. And he finally convinced people that something was wrong with Yoshitaka Fuji's data. That's 12 years after the original flag had been raised that something was very odd in his data. So again, just to emphasize this fact, even when people are committing, this is the biggest fraud that we know about in scientific history in terms of just numbers of papers. Even when people are committing outright fraud, it's incredibly difficult to get journals to do anything about the papers. And he went on publishing more and more and more papers, even after these initial problems had been raised. I mean, maybe they should have not said incredibly nice. Maybe they should have said, or probably fraudulent, and that would have maybe got people's attention. But I think it's just an interesting story that it can take such a long time. And in fact, there's also evidence that even after the papers have been retracted, there's quite a few papers, quite a few analyses of this. People still cite retracted papers. It's a very common thing that papers get citations, kind of post-mortem, you might say, citations after they've been retracted from the scientific literature. So another strange problem, which I think in some sense comes about because of the way that we do our scientific publications. Now, just a few other issues. Now, this is an analysis done quite a while ago now. I think it probably needs an update, 2010. of the percentage of papers that report a positive result. So of their initial, their main hypothesis, how many papers, excuse me, how many papers report a positive result. And in my own field, psychiatry, psychology, that's up over 90%. In other fields, it's still quite high, less so in fields like space science, geosciences. Now, you wouldn't necessarily expect this to be 50-50, but you might expect it to be not 90-something%. And, I don't think everyone is making up their trials like Yoshitaka Fuji, so something is going on here, something weird is happening. And we know, of course, part of that is publication bias. Editors choosing to publish papers on the basis of their results rather than their methods. Reviewers giving an easier ride to papers on the basis of their results rather than their methods. And authors themselves putting stuff in the file drawer when they don't think that it would get published. We all kind of get these ideas ingrained in our heads about which, there's no point in sending that off to a journal because it would never get accepted. So it kind of becomes a self-perpetuating system. And that's one reason, but of course, we all actually still want to publish papers. Scientists are obsessed with publishing papers. And this, and one way of getting papers into journals is to make them look good, even if your experiment didn't look that good. Your study didn't look that good. Maybe it had some inconsistencies. Maybe it looked a bit messy in various ways. As we all know, reality actually is. But there are ways of making it look nicer. And one of the problems that Roger Junior Sorolla, who is a psychologist here in the UK, pointed out was that journals have these aesthetic standards. It's easier to get papers into journals if they look nice. And so this can, as he says in his title, which is a really interesting paper and worth reading, they grease the way through the publication bottleneck, but they're not science. They're not actually, these are things like hiding results that are less, that look less attractive, making sure that some results are relegated to a supplementary material or never published at all, compared to ones that really, underline your message. And you can see this in various things. I mean, we've all heard a million times about power posing. This is the Amy Cuddy study, where this got enormous. Not only has it been cited many hundreds of times, the original paper that this was published in, which is this idea, by the way, that you can do a power pose and it changes your psychology and makes you more likely to take risks and makes you more likely to improves your hormone levels. Your cortisol, stress hormone, will go down. Your testosterone will go up. All these kind of things. Not only was it very popular in the scientific world, but it became very popular in the kind of general press as well. This is a YouTube, a TED talk that got 64 million views on the TED website, another 21 million on YouTube. That was actually a few weeks ago I updated that, so it may well have even more by now. And this is a nice example, I think, of a study which was very low quality when done and very messy and very hard to interpret, but was made to look nice for the journal and got accepted and kicked off a whole, sparked a whole line of these TED Talks, a best-selling New York Times book, all sorts of other great things came to the authors of this paper, or specifically to one author of the paper, because the paper was made to look nice. And the way we know that the paper was made to look nice is that one of the co-authors on the paper wrote a really quite revealing article about how they had changed the analyses and how they did the paper, and said, as evidence has come in over the past few years, my views have updated, and as such, I do not believe that power pose effects are real. So this was the lead author of the paper, not the one who did the TED Talk, but the lead author of the paper coming out and saying, I don't believe in this stuff anymore. First of all, we had a tiny sample size to say that, power poses change people's psychology. Maybe you need more than 42 people. Initially, the outcome was one thing, and then we changed it to other things. or we added other things. We checked the statistical significance of the effect along the way. So 25 subjects, then we added, that wasn't significant, so we added 10 and ran the test again, and it wasn't significant. So we added 7 and ran the test again, it wasn't significant, we added 5. We excluded participants for not following directions, but didn't say in the paper whether that was the case. Of various different statistical tests that we did, we just reported the one with the lowest p-value. We dropped outliers from some analyses. We asked lots of different questions and then just reported the ones that gave statistically significant positive results. So these are all ways of taking a data set and just hacking it in certain ways to make it fit into a journal. And it would be very obvious if all these data were published online and made available to everyone, and the whole process of the analysis made transparent, that this had happened. But of course, this all happened behind closed doors. This all happened in the kind of ivory tower, or whatever you want to call it, of the scientist's lab. None of this got out. And it was only this very rare occurrence that she wrote this article saying, look, I think we did a bad job here. How often does that happen? It was only because of that we know. Well, there are other ways that we know, which is that we can survey people. We can survey scientists on how many times they do these things. And I'm sure you've all seen things like this, but in psychology, in economics, in biomedical clinical trials, lots of people, sometimes majority of scientists in these areas, say that they've done things with their data which we would maybe consider questionable research practices, which would increase the likelihood of them getting a false positive result compared to some sort of more objective or more planned analysis, rather than peeking at the data after you've seen what the results are, or stressing only the significant findings rather than the non-significant ones, and so on. Here's another embarrassing story for psychology. This is an algorithm called StatCheck, which a few years ago was run through thousands of articles, journal articles in the world of psychology, and various different journals, quite popular journals which have decent impact factors and all that sort of stuff. And it was set up to find if there were errors in the papers. So to find if, specifically it was about p-values, and it was one of those situations where if you have the t-value and the degree of freedom, you always know what the p-value will be. And so if the p-value is different from what you expect, then something has gone wrong, something's inconsistent. So this algorithm was able to check that, and it found that in some journals, there were over 50% of articles that were published had some kind of inconsistency in the statistics, and a lower percentage, but still a scarily high percentage, in some cases over 15%, only as low as 6.5%, had an inconsistency that meant that if you corrected it, the results would flip in the opposite direction. So if they were significant, they would actually be non-significant, or vice versa, and would change the whole results of the paper in many cases. And this is all just sitting there in the scientific literature. And again, you go back to what I was talking about at the start. These are very hard to correct, these errors. There's a whole process. You have to put in a correction. It can take months to correct these issues that are just sitting there very, very commonly, as you can see in the scientific literature. Now, I've no reason to suspect that other fields of science will be any better. I mean, maybe some areas are better than others. This is what psychology is like. We do relatively a lot of statistics, I think, in psychology compared to some fields. So you might think that we're slightly more competent than some other areas. Maybe I'm being naive there, but I think other areas, particularly within the biological sciences, would have similar numbers. Was a StatCheck algorithm to be set loose on their papers. And of course, another thing which just to go back to this kind of aesthetics thing about making your paper look good, even if the articles, the statistics are not to your liking. And another thing scientists do often is spin the writing of the papers, right? So when they're writing the paper, there's this big element of subjectivity that comes in, which they're kind of begging you to read the results their way and not the way that's right there on the page staring at you. So we've all seen examples like this, and these are some examples collected by Matthew Hankins. They're real examples of people writing in papers when they've found a result that's not significant at p is less than 0.05, they've found something that where the p-value is above 0.05, so they can't declare the results to be statistically significant, and yet they've written things like a trend that approached significance, a trend significance level, so that was for p equals 0.08, narrowly eluded statistical significance, barely escaped statistical significance, fairly significant, significantly significant, hovering close to significance, all but significant, approaching marginal significance, very closely brushed the limit of statistical significance, and my favorite one, not absolutely significant, but very probably so. Now, these are all things which I think are examples of scientists telling on themselves, essentially. They're saying, like, I want the results to be this way, and I'm going to write my paper as if they were significant, but actually, I can't just come out straight out and say that they were significant. So there's this element of subjectivity that comes into the very writing of a scientific paper. And I think a lot of this has to do with our obsession with journal publication. I really think that paper about aesthetics is a really important one. We all know when we submit an article to a journal, everyone does it. And even if it's difficult to admit this, we all know that when we're submitting an article, we're not just submitting it on the strength of the methods. We're submitting it on the strength of what the paper looks like and what the results look like and how exciting the results seem and how flashy the results seem. And since we all want to increase the size of our CV with lots of papers in Cell and Nature and Science and all sorts of places like that, we do end up in a situation where people are going to be pushed towards bias and pushed towards in some cases, some rare examples, fraud on the basis of this. So this is the classic kind of publish or perish argument. It's not unique to me by any means, but I do think it's a serious problem, and I think we could do better than this. I think science could do better than this. I don't see why we have to rely on a technology from 1665 to continue doing our research. One thing that's been happening in psychology and a few other similar fields, neuroscience and a few other areas, is that we're starting to reform the process of how you submit an article, a scientific paper, to a journal. So rethinking the whole point of a scientific paper, instead of reporting a study that has already been done, now some journals are allowing you to submit just your plan for the study, and it gets peer reviewed. And then the journal says, we'll publish this paper if you stick to what you said you'd do in your plan, regardless of how the results come out. If they're positive, if they're negative, if they're ambiguous, we're still going to publish your paper anyway. And then you go off and do the study, you do the experiment, you do the study, whatever it is, you do the analysis, and then you send it in, and the reviewers see it again and say, yes, this person did what they said they would do. We'll publish the paper, and they do. And this is called a registered report, if you're not familiar. And so that's one kind of tweak to the system we can make. And I think it's extremely important if we're going to stick with the idea of having these standalone scientific papers at the end of the process. This is how they should be done. I'm working on a registered report right now with one of my PhD students, and we keep saying to each other, like, oh, obviously this is how science should be done. Obviously this is how we should be doing our research. But we could do more than that. This, I think, was a very forward-looking and quite prescient in many ways paper from 2012 from Brian Nosek and Yoav Baranan, who there's two papers actually. There's Scientific Utopia 1, which is about the openness of scientific communication, as you can see, and there's another one which is about changing kind of the culture of the way we do research in universities and so on. But in this article, they talked about some things some of which have in large part come to pass, and some of which are still far away or are kind of on the way to becoming real. But they talk about, for instance, having a full embrace of digital communication. So instead of sticking with the old paper system. We can do better. We can change to have things online. I'll talk in slightly more detail about what I think that might mean in just a couple of slides. But they really emphasize this issue of, we're using this anachronistic method to publish our scientific papers. Open access to all published research. So, there's been big strides, of course, in the open access movement, and that's continuing. And this one I think is really important: disentangling publication from evaluation. And this is to some extent what the registered report format I was just talking about does. But what they're talking about is making journal editors into curators rather than decision makers. So at the moment, the journal editor decides whether your paper gets accepted or not, and they have also seen the results of your paper. They've also seen all the details of your paper. Whereas in this scientific utopia that they talk about, scientists would just publish everything that they do. Everything would be 100% open. And then journal editors would come along and say, well, that looks interesting. That looks interesting. I'll take that and have that in my curation thing. One of my friends just set up a newsletter to send out, scientific results that you might have missed, right? So obviously that's still based on scientific papers, but it's the kind of thing, it's a curation, right? She's saying, I think these are really interesting things which you should see. And that could be the way journals go in future. Everyone publishes a preprint. It gets reviewed by an independent peer reviewing agency, and then editors choose among the different papers which to publish in their journals. And that's what they were talking about in this Scientific Utopia article. And they also talked about the encouragement of open, continuous peer review. And again, to some extent, in the past 10 years since they published this paper, this has come true. In a more anarchic, less organized sense, it happens on Twitter. People tweet about papers, and even after they're published, they write a thread on Twitter critiquing the paper and taking apart its methods and so on. And in a slightly more formal way, they do it on websites like PubPeer and places like that, where you can point to errors or issues in papers that you see. And it's all a lot faster than the old school journal thing of, like happened to me when I tried to correct that paper with the weird graph, waiting months to publish a letter, and then nothing actually happens at the end of it. In this case, you would have flags on paper saying, there's been errors spotted in this. Here's the link to the reviews. You can see them all here. So, and the fact that the review is open as well is really helpful. One of the weird problems we have is that so much of the review process happens behind closed doors as well. So I think that's a really interesting article, and one, it's interesting to go back and see what has happened in the last 10 years that kind of makes this scientific utopia come a little bit closer. I think it's still somewhat far off, but somewhat closer than it was 10 years ago, perhaps. Then there was this other article much more recently, last year, in Works in Progress magazine, which is well worth a look if you're interested in this kind of stuff. I've written a couple of articles for them, and there's loads of interesting stuff on there. Where they talked about this, they made the point that a lot of the things that we need to make science better are already happening, but they're happening in very specific fields. So we can learn a lot, we being the generic scientist, can learn a lot from different fields that are not ours about the way things work. For instance, in psychology, we've been using preprints just for maybe the last 5 years. They've become quite popular. But of course, in physics, preprints have been completely normal. Posting your paper on archive since the 90s. And also in economics too, they publish working papers, which we would never really consider in psychology up until recently. And then having kind of open review of those and general discussion. And it takes a much longer time for the actual paper to get published, but that doesn't matter because the results have always been out there for people to discuss and for people to base any subsequent research on. They talk about protein folding, where there's these enormous databases being built up over time. Instead of the results all being scattered across many different journals and different websites and so on, there's these big centralized databases, which when a new technology comes along, a new algorithm, a new way of doing analysis comes along, it's easy to feed that method the data. In this case, there was the AlphaFold research from DeepMind that made some major strides in our understanding of protein folding, which was reliant on these big databases of different proteins existing. In statistical genetics, it's become completely normal to share the results of your analysis. So if you're doing a genome-wide association study, it's very common to share the results around the community and use them to use other people's results to build into your analysis and so on. So that's a very, very common thing. Also, another thing we can learn from statistical genetics is collaboration. When your sample is too small, you work with many other scientists across the world to build up a much bigger sample, increase the statistical power of your work, and actually make it much higher quality. From computer science, there are some journals in computer science that are entirely based on version-controlled sites, and I'm going to talk about that just on the final slide in just a moment. And in clinical trials were the first field of science where it was mandated that you register your analysis plan and you register your plan for the trial. There are still lots of problems with that. People not doing what they said they would do in terms of the outcome that they use or the analysis that they run or whatever it is. But we can learn a lot of lessons from what happened in clinical trials. And finally, then, perhaps, at least in some areas of science, or at least for some types of research, we might move to a system where there's no such thing as a journal, or it's not a journal in the way that we have it right now. It doesn't have scientific papers published in it. It has living documents. So instead of the living fossil that we have right now, which is a scientific paper, we have living documents based on something like GitHub. So there's this interesting article in 2019, which is worth a look, that talks about how we could completely rejig the scientific publication system on the basis of something like GitHub. So journals become a collection of repositories on GitHub where people can easily publish their research just by clicking a button. They don't have to spend a whole day going through the clunky journal submission process that we've all done a million times. Editors, again, curate these rather than make decisions on what gets published and what doesn't, which I think is really important. There are reviewers, and again, you can create organizations for peer review that give a score to particular, this particular repository, this particular analysis is really good and really high quality, and so on. Revisions and additions, it's version controlled, right? So anything you change about the paper, you can see that's happened. It's easy to add new stuff. Maybe you're running a longitudinal study where a new wave of data is going to come in a few years. You can add that to your living document paper much more easily. Maybe there's a new type of analysis comes out that maybe the way you did your analysis was not correct. You can rerun the analysis, and it's all saved there in the system. It's all transparent for anyone to see. Anyone can come along and reproduce your results because presumably you would share the data as well. And there's a whole system on GitHub already for when people write their code on GitHub. There's already a whole system of rewarding higher quality code, better annotated code that's more widely useful, whatever it is, with kind of reputation points. More people look at the GitHub repositories where there are there's higher quality code, and so on. So it's not like this is a completely alien world where we would remove all the incentives that scientists want for doing good work. It actually has a system built in already. Now, obviously, these are kind of fantasies at the moment. These are not things which we couldn't just tomorrow just turn the scientific world into one big GitHub. But I do think these are things to think about and to experiment with on a small scale. We're very, there's a weird sort of paradox between, on the one hand, scientists are meant to be about experimenting and trying new things and seeing what works and actually gathering evidence for what is the best way to do things. But on the other hand, they're quite conservative, and with a small c anyway, and quite subject to inertia in the way that they do things. So I think there's lots of room for experimentation to bring ourselves a little bit further away from 1665 and a little closer to 2022. So thank you very much for listening. I'm happy to take any questions. That's me done. Thanks.
Thank you so much for this interesting overview. on this problem. I think this perfectly fits also with the other two contributions we had before. So I think we could start our question and answer session specific for this talk, but also if you want if you have also other questions related to the other talk, we can also have this kind of open panel of discussion. Bastian, yes, first.
Okay, can you hear me now? Yes.
Yes.
Yes. Thank you, Stuart, for this presentation. I think it was very nice to hear about all of those problems and how we could improve about that, how we could improve things in general. I would like to have your opinion on a saying that says that that science should be open as much as possible, but as closed as necessary. And what's your view on that? Especially, I can relate to, for example, what happened with COVID, when we have had a huge amount of information, a huge amount of scientific articles which have been published, or let's say released in preprints, and sometimes misused by, let's say, the overall community. And so, what's your view on that?
Yeah, we did have a big problem with that, and I do think that there are some downsides. So yeah, there was. I remember at the very, very start of COVID, there was all, and it was a kind of a it kind of heralded. There was going to be this huge debate that went on for years. There was all this stuff about how the COVID virus is very similar to the HIV virus. Do you remember that? There's a preprint that appeared that said that, and it must be man-made, and it must be and that was a preprint, and it got covered, and people on Twitter started tweeting it and so on. But I think the system that we have of rapid peer review and so on, post publication or whatever you want to call it, peer review. I mean, that paper was immediately trashed online. That paper was immediately shown to be completely inaccurate. People did all these long threads saying this isn't right, this isn't right, and so on. So I think that's a big part of it. Is that you open up the system and make it faster, but it's also faster to take stuff down. I also think the advantage of preprints at the very start of COVID, where people were passing around legitimate information on new ways of modeling it, information on the virus's genome, for instance, I think that was so useful, and so useful for other researchers, that I think it balances out some of the misinformation, or whatever you want to call it. But yeah, I do totally agree that there are going to be downsides to this. I think we have to develop a system where and by the way, there's also downsides to the criticism thing, right? People can criticize articles, especially if they're anonymous online, for bad reasons, for nefarious reasons. If you're having people come in and do like peer review of other people's articles, people can do it for bad reasons. Maybe it's your rival in your other lab. Maybe it's someone who's obsessed with you in some way and wants to destroy your research. So there has to be ways, and I'm not saying I know the answer to this, of having some kind of reputation management, or I don't necessarily think verifying people. Maybe that's one thing we could do. I think there's a debate about anonymous versus named people, certainly within the context of peer review. So yeah, these are all questions which need to be answered. But I think the answer, the way we answer them, is to do some experimentation, to try out these new ways of doing stuff before we kind of jump in and say we must change everything in science right now.
Thanks.
Thanks. Other questions? So I have actually a question that relates to the title of this workshop. That means that I think we heard about this view of the problems of the paper itself. Before we attended two kinds of solutions. I would want to ask you whether you think that there is that might be nowadays that it's all online. This kind of solution, which is called explorable explanations. So it's something that you have sort of like, for example, a notebook online where you can explore the results and, for example, start playing with the thresholds, and you put on the Instagram one variable with respect to another, and so on and so forth. So my point was to ask you whether you think this could be way beyond the paper, because there is no, let's say, gatekeeping on what the original scientists want to communicate, or if this could be a way to make that kind of research, which is going to be disseminated, even more, let's say, reliable and useful for the person that is exploring the actual result.
That journal that I mentioned that does the registered report thing, which is Cortex, was the first journal. It's a neuroscience journal. Now doesn't just have the registered reports thing, but has a exploratory reports thing too. So you can submit an idea that you're just gonna mess around with the data. You're just gonna try stuff out. And my immediate thought upon seeing that was, well, if people can just mess around with the data, wouldn't they just end up finding false positive things and claiming that they were, you can imagine a situation where you just mess around with the data, and if you find something, you send it off to Nature. If you don't find something, you send it off to the exploratory reports part in Cortex, right? So you can imagine. So there's this weird thing about needing to pre-register your exploration, which is a kind of a strange, again, another kind of paradox. And I think that would apply in this case. I would worry a little bit about, people publishing stuff because they've spent hours fiddling around with every possible combination of analysis in this someone's data. So we'd have to have ways of slightly controlling that. Maybe if it's just people posting their plans for what they're going to do. But I do think there's this there's a tension between exploring stuff and having it completely open, and trying to keep false positive rates down and stop making mistakes and so on. And again, I don't know the answer to that. And as we become more open in future, it's going to become trickier to do this. I don't know if anyone else has any kind of views on this issue.
Sure, feel free to jump in.
I'm not sure I have correctly understood the starting point, but from what I understood is to be able to have the data and play with it directly within the article. No? Yeah. So I think that eLife has done something like that recently. One or a couple of years ago, they have tried to implement this, and directly in the paper, when you click on the result, you can directly see where it comes from in the code and where it comes from in the data. So it's very helpful for that. And I think it was a very nice initiative, and something with the online editor we are developing in Insight. This is something that we would like to implement as well, because it shows off. It's full transparency here, and I think that's exactly what science needs.
Yeah, I agree. I think making sort of explorable data sets is really just a slight advance on open data. I mean, bad open data is just putting a messy, horrible raw data set into a repository, and making it clean and reusable and embedded in some code is just the proper way of doing that. So I think that is an advance. But what I think to Stuart's problem with the allowing people to essentially p-hack data is that we have to break that link between making findings the be all and end all. We have to start judging on intrinsic quality of work and not on extrinsic implications of work. And until we do that, I think we're always going to have that problem. But the moment that we do judge on intrinsic quality, I think we remove a lot of that problem. So I think that's what we need to square up to.
Thank you. Are there any other questions or comments to drive, possibly drive the discussion in the open panel?
Maybe I can pose a question to Stuart. A lot of the solutions that have been suggested, like making scientific publication more like GitHub, which fills me with fear. I am not a GitHub fan. I am not a geek. I don't work like that.
Yeah.
Do you think that that there's a potential for making some areas of science that are more quantitative and are more used to working in that kind of code-based environment, very different from areas of research, not just science, but research, which don't work in that way.
The second half of that Speed of Science article that I referenced is directly addresses your question there. I just didn't mention it in my slides, but they say, and I'd be interested to view on this because I don't know if this is the answer, but this is their answer to this point, is that the answer is specialization. So in lots of other areas, we don't expect people to be able to do the coding and the statistics and the data collection and the writing and the dissemination and the, everything else, which we do in science. We expect everyone to just be able to do every part of that, of the process. We have author teams and so on, but in general, scientists are expected to be able to do all these different things. They are arguing for higher levels of specialization. So you have people in whose only job is data curation, or only job is statistics. In clinical trials, they give the analysis to statisticians often. It's not that the scientists themselves are running the statistics. Whereas in psychology, the scientists themselves run the statistics all the time. They're the ones that ran the experiment. They also run the statistics. They also write the paper. They also do all this. So what they're arguing for in this article is a higher level of specialization. So you would have people on your team whose job it is to make the stuff go online, make it all work, make it reproducible, make sure the code runs and so on. And actually sharing code among a team is very helpful in that way as well. The sort of co-pilot idea where you get someone else to run it just to make sure that it works on their computer and not just yours. So that's there. I don't know, how far that goes in answer to your question, but that is what they would say. And I think I agree that in science and actually in academia more generally, there's a very high degree of specialization, a very high anti-specialization, generalization required, where you're, and it's not just within the actual research process. You've got to be good at doing admin. You've got to be good at being a teacher. You've got to be good at, leading a team and working with your students and, all this other kind of stuff. To some extent in my university, for instance, they've now they've introduced teaching only lectureships where you're not required to do research. That's just not part of it. You don't have to think about that. You can focus on just being a really, really good teacher. And I can imagine in future bringing in research only ones where you just teaching is not part of the thing and you can specialize a bit more. So I think more specialization probably to some degree answers that question. But yeah, I agree that there are going to be some areas where this is scarier than others. And that's a huge part of it. Brian Nosek wrote a blog article about changing the culture of science. And one of the kind of biggest things we need to focus on is making it easy. Not just kind of shaming people for not doing it, putting their data online, being transparent, pre-registering, all that sort of stuff, but is making it easy to do these things. And that's what he's been doing with the Center for Open Science, is trying to make the website work in a way that anyone can go on and use it. But it even just a few years ago, even just a few years ago, that website was extraordinarily difficult to use, and now it's a little bit better, but maybe not quite as good as it could be. So there's a lot of work still to do to make it easier to live up to these goals.
Yeah, no, I mean, I agree, and you probably know I agree that specialization is when I came back to academia, I was kind of shocked at the lack of professional specialization, in that it's like, I do not want my airline pilot to be building the plane. Why are you doing statistics?
That's a nice way of putting it.
I want the experts there. I don't want my expert surgeon to be doing the statistics and therefore cocking it up just because they've watched a YouTube video on doing a t-test. So, it's shocking to me that people don't consider these things as important professional specializations. But I think when it comes to dissemination, the idea behind, not dissemination, sorry, the sharing your work, I think we have to make these platforms extremely user-friendly, because for non-technical, non-geeky people, because you want those people to be in control of putting their own work out there. So I don't want to have to turn to a team member to say, can you make Open Science Framework work for me, please, because it's a nightmare. I agree it's not quite such a nightmare now, but still, every new person I introduce to it, I have to take them through how to use it. And that's not good design.
Yeah, I agree.
Possibly they didn't specialize in getting in a user design.
Someone who was good at UI, exactly.
Yeah, I also think we're discussing this also in this morning workshop we had about data sharing. We also need, there are nowadays lots of these kind of middle profiles, something in between, for example, scientific research and IT and data management and so on and so forth. What we would need is to have at least a common language. This morning we called it an interoperable language in order to have like a standard way to deal with problems. But I think many of the initiatives you mentioned, for example, the step-by-step register report or your way of approaching all the scientific production routine by dividing in small steps, so something that reduce the discussion to single unities is something that maybe is going in that direction as well. I have one last question, which would be directed to Alex, but I think it's worth discussing for everyone. So you mentioned the role of UK reproducibility network. Having said it, you mentioned it as the UK version of the Italian reproducibility. I think it's quite the other way. So UK reproducibility network was a great inspiration for me and Carlo Mignussi. We are two of the Italian founders of the Italian reproducibility network. And my point was to ask you whether these so if you found there let's say a sort of an environment for scientific growth, so something that supports you in the scientific aspects of your initiative, or more like something that supports you in the let's say the administrative problems, in the technicalities and so on and so forth, and whether you think that this problem of for example, publications or integrating different knowledge into the research production should be supported by initiatives like this, for example, networks or a foundation, or in any case, containers that try to collate different points of view.
So I think coming up with different ways of doing scientific publishing, as we've heard today from all speakers, is not the difficult bit. There are lots of ideas out there, and building platforms is also not the difficult bit. You know, this is not rocket science, and academics can do this kind of thing. The problem is the politics and making things actually work in principle, which actually academics are often not very good at, because that's not their job. They do the research, they come up with the ideas, they do something in principle, and then they publish a paper and go away and never do anything with it. And so the difficult bit is now to move things from good ideas and prototype platforms into something that works, and something that works at scale for and that everybody uses. And that's the point where things like UK Reproducibility Network and DORA and UKRI and all of the bigger organizations and the political institutions are really important. And so that's where I still have hope that when we launch next week, that we won't just be another initiative, because people like UKRN are there in the background. They are making sure that people at the tables at all of these institutions and people discussing the future of research assessment are all aware of Octopus and have all fed into Octopus, so that I've heard the potential problems, I've tried to take account of them. Obviously, there are going to be things that we haven't predicted and haven't thought of and that we'll need to change. But I think organisations like UKRN are absolutely vital to the success of initiatives, because it's all of that. I mean, you put it as administrative, but it's far more than administrative. It's the kind of knowledge exchange and small p politics, as I said before, that's really, really important to making something practically work and not just practically work, but sort of socially work. So that's where they have been incredibly helpful. Marcus Manafo is a hive of information. You only have to drop him an email and say, who should I be talking to about X? Do you know who can help me with Y? And he can say, here you go, and here's an introduction email to them. So that is the most invaluable resource that the backers of Octopus have given. I mean, I'm incredibly grateful for the funding from UKRI, but the funding wasn't the barrier, as it were. The barrier is the social acceptability and trustworthiness of a platform. And that's what I think these sorts of institutions can help give. So that's where they've been a real help and will hopefully continue to be, because that's what we need in the next few months as we go live.
Thanks. So I'd say that we hosted a talk by Marcus Bonafont 2 years ago online. We were right in the middle of the pandemic, and he was a great inspiration for developing the Italian representativity network. I don't know if you want to add something to this.
Well, they're absolutely a huge inspiration.
Yeah. Also the other speakers related to public institutions supporting the new ideas. So.
Yeah, all I can do is echo that. I think I agree completely about Marcus, and I agree that all these institutions just I think just having people being aware that these things exist and that there is such a thing as the UKRN and so on. That's harder. It's harder than you would think to get across to people. So we're in kind of a bubble of people who are interested in this topic, and it's easy to think, oh, everyone knows about there's a UK reproducibility network, and we have a reproducibility club at our university and all this kind of stuff. But actually, the vast majority of people, or some large number of people, have no idea about this sort of stuff. So making those social connections is such an important thing, and just pointing people in the right direction of, oh, you can get help with making your science higher quality, or you can get help with putting your data online or whatever else, just by talking to this person or talking to this person. So I think that's an underrated aspect of it, is not just having lots of money to build nice websites, but actually linking people up and having some kind of social connections there. I think that can encourage a lot of people into this world that wouldn't necessarily otherwise be into it, just through inertia or through being too busy or through just never really thinking about these issues in some kind of systematic way.